So maybe quick complexity recap. I'll try to write larger than average letters, but if you can't see, you really should come closer. I don't think we have much of a choice. So I'm gonna constrain myself to mostly graph theory problems, and so I'm gonna sort of assume that G is a VE. Think of that as a simple graph, and A is gonna be a subset of edges. So I wanna think of a class NP. That's a very formally defined class. So this is a class of problems that exist A such that phi of A equal to T, where T stands for the truth. So let's try some examples. So for example, you can have phi of A equal to T if G is planar, in which case you're trying to find A, which is a spanning tree. And you can ask instead of planar, you can say G is Hamiltonian. In this case, A is a Hamiltonian cycle in the graph, or you can look at G contains perfect matching, so A can be a perfect matching in the graph, and so forth. So that's my class NP. So class NP is a class of problems where the decision. So the really important part is phi of A. T is in polynomial time. Okay. So it's, and by analogy, let me try to push this up. Sharpie is the number of A such that phi of A is T. So this could be the number of spanning trees, number of Hamiltonian cycles. Let me write that. Number of spanning trees in G, number of Hamiltonian cycles in G, or number of perfect matchings in G. Okay, that's a very formally defined class. So for every graph, you're trying to decide if it has a Hamiltonian cycle, and you're looking at a subset of edges. You're looking at them, and it takes polynomial time to decide if that subset is indeed a Hamiltonian cycle. Okay? Yeah, correct. So here, thank you, Avi. It's an important to emphasize. Input is the graph itself, which is given as a list of vertices and edges. And in a similar way, you can write many other classes. Maybe I can actually use, let me see. I'm told I can do this. So in a similar way, you can write. I just want to make sure you know what are those things that we're talking about. So there exists an A such that for all B, we have some property of AB equal to T. And the polynomial hierarchy is even more complicated. So there exists for all, there exists for all, ... and that's K times. And then we have something, ... equal to T. Okay. for some fixed k. Yeah, so this is, well you would get sigma k for fixed k, but this is for k greater or equal to 0. So sort of the union of all those classes is a polynomial hierarchy. And so when we say that polynomial hierarchy collapses to sigma 2, it means that all those very complicated problems with lots of quantifiers can be solved with just 2 quantifiers. And that's considered to be unlikely. Okay, so let's leave that. Now, I want to recall some problems that we did last time. So last time we looked at for example, at a combinatorial interpretation for number of partitions divided by 5. You remember that? This is you're really far away. Somebody say yes. Okay, so this is a number of something, but in reality, this number can be computed in polynomial time. Do you know that? Say yes if you do. Oh my. I guess you don't. You really don't. So let's see. P of P of n. The definition is that's a number of partition lambda partitions of n. Okay. So what one can do is write P of n is sum of P of n m, where m from 1 up to n. What?
It's reflecting and it's harder to see there.
I cannot do anything really. I think there is a theorem that now, no matter where I write, one of you is not going to be able to see. So let P and M be the number of partitions of n, where the largest part is m. Then clearly P of n is the total sum of those, and in fact there is a sort of trivial recurrence relation for this. This is equal to sum over all I from 0 to n minus, well, from 1 up to n minus m, P of n minus m I. Okay? So now what you do is you quickly compute all those numbers, and that gives you that number. Once you have that number, so this is what people call a special case of dynamic programming, but it's really a simple recursion. And once you have that, this implies that this number really can become, if it can be computed in polynomial time, then of course this isn't sharp P, because there is a trivial combinatorial interpretation, all numbers from 1 up to this number. You see what I mean? So it's not so here is a combinatorial interpretation of numbers from 1 all the way to 1/5 P of 5n minus 1. So now you have to ask yourself, do we like that? No. Is that a combinatorial interpretation from my point of view? Yes. So remember the feeling of not liking something. It might happen again for you, but the point here is that this shows that proving that something is not in sharp P is actually extremely strong. It also shows that you cannot do these simple things like here. Okay, so that's one of the points I wanted to make. On the other hand, if you look at mk of g squared, so those are k matchings minus mk minus 1 of g, mk plus 1 of g. So this number is not going to work like that. You should not be able to compute that fast at all. It is not too hard to see that this number is actually Sharpe complete. Sorry, actually the whole point is this is, yeah, so Sharpe complete is fine. So this number isn't Sharpe by the proof I explained to you, but it's actually complete. Both. But it's a good idea to start with that. And the reason is the total sum is the total number of matchings, and that was known to be Sharpe complete for a while. So what we're saying is this trivial trick that we're trying to do here would not work. Okay? So we know that this is Sharpe complete, and that's why this problem is much more interesting. And similarly for the forest numbers, fk of g squared minus fk minus 1 of g, fk plus 1 of g. So this is this is Sharpe hard. So Sharpe hard means that every problem in the class Sharpe can be reduced to this one. Okay, so given some other graph H, if you need to compute Hamiltonian cycles, there exists a graph G for which this difference is going to be that number of Hamiltonian cycles. This is not precisely true, but roughly speaking.
By the way, the summation should be up to n, right? Not up to n minus.
No, it should be up to n minus m. Oh, up to n. Up to m, correct. Okay. Everyone good there? So what I just told you is even though there is the connection between Sharpe completeness and being in Sharpe is relatively weak. So both of these problems are Sharpe hard, yet this one isn't Sharpe and this one we don't know but believe not to be. Okay? It is important to check whether you can compute this in polynomial time. Okay? So this is end of the recap from last time. So now I wanna tell you kind of the end of last lecture, the end that I didn't get to tell you because I was overwhelmed explaining other stuff. So what are our goals? So main problems. So so before I do that, let me tell you kind of problem 0 that is solved, and this is Littlewood-Richardson coefficients. Richardson coefficients, and so the Littlewood-Richardson coefficients C lambda mu nu. Now, the way we define them is we look at sure polynomials x1 up to xn. Well, let me put here mu. And and this is equal to summation over all partitions of lambda, C lambda mu nu, S lambda, from the same x1 up to xn. Now, I wrote, so those are sure polynomials. And so how do we understand that? Sure polynomials, you should think of them as characters of GLN. Okay? when you take a product that corresponds to tensor product of two characters, these are characters of two reducible representations. So they split into other irreducible representations. So we conclude that this is a non-negative integer. Okay? And once you write that, it's a natural question to ask, does this non-negative integer have a combinatorial interpretation? And the theorem slash corollary is that C lambda mu nu is indeed in sharp P, because that counts number of certain tableaus. Okay? Let me not tell you what kind of tableaus. This is slightly complicated and involved, but I do want to say that this is a miracle. The fact that this theorem is true is a miracle. There is no reason for that theorem to be true other than the fact that it is. And it was introduced. The rule was introduced by Littlewood-Richardson in 1938, and it took until about 1980 to actually make this into a real theorem. It took a while. And so the key person here is Schützenberger, who invented technology which allowed to prove that this is an actual combinatorial interpretation. Now we have many proofs of that result. Okay? But back in the day, this was a pure miracle that took a while to understand. And so this is a solved problem. And by analogy, there are two unsolved problems. One is about Kronecker coefficients. This is the one Greta was talking about. And the definition is extremely similar. So we're going to do the same thing, but for the symmetric group instead of GLN. So those are GLN characters, and now we're going to look at the symmetric character symmetric group. We're going to write chi lambda chi mu as a sum of g lambda mu nu chi nu. Okay, all of these are partitions of n. So lambda mu are partitions of n. And for the same reason as before, those numbers are going to be non-negative integers. And it's an open problem. I'll write it as my own conjecture. So my own conjecture would be that g lambda mu nu is not actually in sharp P. Okay, and if you did not follow this formula, there is a kind of different way to write it, I suppose. G lambda mu nu is 1 over n factorial sum over all sigma in Sn, chi lambda of sigma, chi mu of sigma, chi nu of sigma, which shows that they're symmetric, of course, but it also gives you kind of like an easy way to see what these numbers are. And of course, once you write it them, this is by definition. There is nothing happening here. Once you write them that way, it's not even clear that they are not negative. Why should they be? Well, they are. Well, actually, it's not even obvious that they're integers, but they are for a simpler reason. So, so there are many reasons why people actually want this to be true. They want this to be in sharp P, and that's because they want to prove results similar to the ones they proved for Littlewood-Richardson. One of the famous one being saturation conjecture that Knudsen and Tau proved using very explicit form of a combinatorial interpretation for Littlewood-Richardson coefficients. However, we don't know basically how to do that, and Greta and I wrote a lot of papers trying to figure out what Kronecker coefficients are. So so some of that she mentioned during her talk. So
one more unsolved problem are. This is full symmetry, yeah. In fact, there is more than full symmetry. Somehow, if you can conjugate any two of them, it's still going to be the same. If you, that corresponds to taking tensor product of each of the two, any two of the characters with a sign. So somehow there is just a remarkable symmetry involved here. Those are beautiful numbers, and really complicated. And so maybe before I say what I'm about to say, let me mention that those numbers will already. I'm just going to repeat what Greta said. Littlewood-Richardson coefficient decision problem, whether they're zero or not, can be done in polynomial time by Knudsen-Tau theorem. While the numbers themselves are Sharpe complete and in unary, that's what we believe. We don't have actually proof of that. That's a conjecture. In this case, this Kronecker coefficients are Sharpe complete in unary. That's a theorem. So there is already some evidence that those numbers are much harder, but we don't know how to prove that conjecture. So there is one more set of numbers that we like to explore, and those are Schubert coefficients. So defining them is a little bit of a challenge, which I'm going to fail probably. There is a chance that you know this better than I do. So I'm going to write it in a slightly vague form. So those are Schubert coefficients, which describe cohomology theory for the complete graphs, for the complete flex. And the way you should think about that is that this is a number of intersection points in the intersection of Schubert varieties SU, SV, and SW, and you need to perturb them a little to avoid some degeneracies. So this is a number of points in the intersection. Okay? And if you don't know what I'm talking about, I think you'll survive. It's going to be fine. Okay? Just wait 2 minutes and it will be over. So one thing that one should know about this, I'm going to try to write sigma this way, that those numbers do describe structure constant, just like Littlewood-Richardson and Kronecker coefficients. They describe structure constants in some ring of multiplication. They also describe structure constants. So you can write sigma u times sigma v equal to sum c u v w sigma w. So where the summation is over W, all of these are permutations, and those are Schubert polynomials. And those Schubert polynomials, so they have an explicit description. So as a sum of, there is a combinatorial rule to write them down, which I can do that if you want me to, but I'd rather not, which tells, which shows that this is sum over certain tableaus, x to the number of tableaus, and those polynomials, I should have said that these polynomials sit in C of x1 dot xn. Okay, and in fact, as polynomials, they have non-negative integer coefficients. So we have very explicitly defined this is a real theorem. Here that we have an explicitly defined set of polynomials, and we're looking at a structure constant and the multiplication of those polynomials. And in the same way that we did before, we can, let's see. In the same way we did before, we can ask, is it true that they're in Sharpe? So So the conjecture is that C U V W is not in sharp P. That should be the right conjecture. And we're not super close to proving that. All we know by now is that those numbers are actually in the polynomial hierarchy. So decision problem whether these numbers are zero or not in the polynomial hierarchy. And that's my latest result with Colin Robichaud in preparation. So I'm not going to say anything else about either of those problems, but I do want to write this as a, I did want to present this as a goal why I'm doing everything I'm doing. Is this clear? Go ahead.
The way you define these Schubert coefficients is not combinatorial because they're continuous brackets, but they are counting something.
Yeah.
Are the protocol coefficients counting something? Maybe we didn't.
That's not how you should, they are counting something, but that's not how you should think about it. So they are counting an invariant space under some action of GLN. So is a dimension something which you're counting something? So they're not counting anything nice. That's the point.
Nice being that membership will be determined.
Yeah. So yeah, I can tell you much more, but I'd rather not. Go ahead.
But if you embedded the Schubert varieties in some projective space or something like this, you couldn't tell them polynomial time. No, I guess they're continuous functions, so it doesn't make sense.
So that's part of the point. The point is that you cannot make it into a formal framework of the usual complexity theory, something that you can do over complex numbers. So there are substantial difficulties when you do this conversion. It's not like a small thing. So there is a reason. So Schubert coefficients, Schubert polynomials go back to Schubert in 1880s. None of this is a recent thing. So people have been studying and writing fancy papers and fancy journals for a long time by now, trying to understand that. And until recently, they couldn't even formulate the negative question. Colin might not like the fact that I'm telling you this. So the theorem that we have is that CUVW deciding whether it's zero or not. I'll write the truth, and I'm not going to explain the truth. So it's in a relatively low complexity class, which is sort of like sigma 2. Okay? But deep down in the polynomial hierarchy. And this is assuming GRH. Well, you have to assume something. Is that okay if I move on? Because those who don't know Schubert polynomials are not going to know. And those who do are going to be bored otherwise. So I'm gonna start erasing all that. So last time I mentioned that we showed that, well, I'll write it. Square is not in sharp P. So this was our theorem with Ikenmeyer and Greta, assuming pH is not equal to sigma 2. Okay? So I told you that this is true, and basically, I hinted how we do it. So essentially, essentially what we do is we can show that this number, which it can be written as so the problem. Let me write it more carefully. So the decision problem, whether this is 0 or not, is turned out to be very difficult, and one can reduce a problem where the number of Hamiltonian cycles in G minus equal to number of Hamiltonian cycles in H. Okay. So in reality, what we're doing here is what we're doing here is we're studying a polynomial x minus y squared. That's what goes into the proof. So somehow you should now look at all these functions that I present. Maybe I can write that here. All those functions lie in the class gap P, which is sharp P minus sharp P. So both character Schubert coefficients, Kronecker coefficients lie in this class gap P. This is not super obvious. In neither of these cases, this is obvious, but it's true. You can sort of imagine why it would be true if you're for Schubert polynomials, because if you can write them explicitly in terms of monomials, then you need to do a Möbius inversion. And it turns out that you can do a Möbius inversion effectively in a way to show that it's in GAN P. So rather than explaining this theorem, what I'm going to do is I'll mention some much simpler theorems than that, and you'll see you'll see how we do this. So let me see. I found a really simple framework from which to put. Let me start erasing here. So here is a different problem that permanent quadratic inequality. So what I'm going to do is I'm going to write a very simple looking inequality, and the inequality is going to go like that: permanent of x1, x2 dot 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 xn, y1, y2 dot 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 yn, and the rest I sort of don't care. There is a whole bunch of things with z square greater or equal than. I'm going to explain what I'm doing in a second. So this is going to be x1, x2 dot 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 xn, x1, x2 dot 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 xn. Everything here is z times permanent of y1, y2 dot 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 yn, y1, y2 dot 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 yn, and again z. So suppose xi, yi, and all those zij's are non-negative real numbers, then we have that. That's a simple inequality. Okay? So if you like geometry, this is very special case of the Alexander-Fenn inequalities where all polytopes are actually bricks. Okay? Are boxes. So permanent is a mixed volume of a first convex body is a box x1 by x2 by dot 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 by xn. The second is similar with y1 and so forth. So we have n convex polytopes, which are all boxes, and we're writing Alexandrov-Fenk inequality for that inequality, for those convex bodies. You get this inequality over there. This clear? And now, just like we've been trying to do before, you're asking, does this inequality have a combinatorial proof? Okay. Permanent of that. Permanent square is greater or equal than the product of two permanents.
Here you double the x's and here you double the y.
Correct.
That's the difference.
Yeah, that's the only difference. For all these. And what I want to say is no. So let me try to make an argument. What I'm gonna so the more you stare at it, the more you don't understand what you're doing. Okay. So what you want to say is, suppose xi, yi, and zij. Suppose all of those are sharp p functions. Okay. So you should think of each number as a number of Hamiltonian cycle of some graph. Okay. And now when you subtract the right side from the left side, so when you're going to look at the defect of this inequality, that's going to be a non-negative polynomial. Okay. But it's non-negative in the sense that its evaluations at xi, yi, etc. are going to be non-negative at each point. So, okay, but now the question is, would that function? So at the end, you get some kind of p polynomial p of all those variables. So we know that it's greater or equal to 0. And now the question becomes, is this polynomial greater or equal to 0 as in a sense that when you substitute here sharp p functions, is this a sharp p function? Let me, so this is my notation for is this polynomial in sharp p for all sharp p functions over there. Okay. And the answer, as you can imagine, no. But let's try to see why. And once we kind of understand that, so the answer is no. And let me explain what's going on. Yeah. But you've seen it here. This polynomial has negative coefficients over there. It's so this polynomial is greater or equal to 0. However, the square does not have a combinatorial interpretation unless pH is equal to sigma 2. Let's try to understand it in this case. It's going to be very, very similar. And I promise you can follow this. I know this looks like a giant product of permanence, but even before I do that, the natural temptation would be to think of that as a collection of perfect matchings. Just like with K matchings that we had before, you can try to take one perfect matching corresponding to the first permanent, to the one in the middle, one perfect matching corresponding to that one, and take an injection to the one on the left. Okay. So what I'm going to say is under certain assumptions, it's not going to work. And let me try to do this carefully. I have it written somewhere. Oh yeah, here we go. No. Yes. So let's take n equal to 2. Let's take y1 equal to y2 equal to 1. So we have a permanent of x1, x2, 1, 1, greater or equal than permanent of x1, x2, x1, x2 times permanent of 1, 1, 1, 1. Yes. Correct. Okay. And now we calculate what is that? That is x1 minus x2 square. Sorry, plus. Correct. Yeah, determinants are hard to kill. So we're saying that this is greater or equal than 4x1, x2. So that is equivalent to saying that x1 minus x2 square greater or equal to 0. What? I think this is supposed to be correct. 2.
X1, x2 plus x1, x2. X1 is 2 and 1. X1 is 2, x1 is 2.
Yeah. So what did we conclude? That this inequality cannot be proved under the same assumption that pH is equal to is not equal to sigma 2. So to make it a little more formal, if you have a polynomial like that, if you substitute into this polynomial generic Sharpe functions, okay, then you should not be able to give a combinatorial interpretation for that. So that function is not going to be in Sharpe. Okay, and everything I'm saying can be made very, very careful. But before we do that, I want to consider a different example. Is everyone okay with this example? Ramon? No.
Understand the implication that you're trying to. What implies what?
Okay. So I'm.
This is x1 minus x2 squared is greater than 0, the special case of the permutation.
Correct. And that special case already cannot be. So this inequality cannot be proved combinatorially. Yes, that's the proof. So I'm using here the same argument as I was using over there. So I'm reducing it to the same problem as here. Yes, yes, and that one I didn't do. Correct. So I didn't do, but I did hint to that. So what I'm saying is, excuse me, if you have a combinatorial interpretation for the square of difference of two Sharpe functions, then you have a witness polynomial witness for non-equality of those two functions, and that is impossible for general functions, and this requires a theorem. Yeah. So let me. Right. This is something I really don't want to write formally, but so theorem. Let's do that carefully. So deciding. So suppose deciding if f is equal to g. Suppose that is so deciding if f is not equal to g. Suppose that is in NP. I don't know one. Sorry. So suppose then pH equal to sigma 2. I think that's fair. If f and g for all, so suppose this is for all f g sharp T function. Well, if it's for all, then in particular it's for sharp P hard. Okay, so suppose this is known for all sharp P functions, then we get this collapse. Okay, so we're saying that for some xi's you can maybe get combinatorial interpretation, but for general xi's you should not be getting combinatorial interpretation for the square. Because if you could get a combinatorial interpretation, then this would imply that that this problem actually has is actually an NP. And if it was, then you would get a collapse. Okay. And that leads to an interesting and very deep question. So while you're completely stunned with this knowledge, one can ask the following question: what happens when you have more complicated polynomials than that? Can we describe all polynomials? So formal language would be all polynomials which would give a closure properties for sharp P functions. And the answer is yes. And that's what I want to explain. But before I do that, let me give a positive example. Let's do it here. So a positive example would be Fermat-Little theorem. So Fermat-Little theorem says that suppose P is a prime, then and A is an integer, then A to the P minus A, then P divides A to the P minus A. Everyone good with that? Now what we're going to do is we're going to ask: is it true that 1 over P A to the let me put here variables so it's a little easier to think about. Is that polynomial? Does that polynomial have a combinatorial interpretation? Yes? I'm asking. What? Well, it is equal to something. But
like the standard pizza explanation.
correct, correct. It's not a pizza, but yes. Let's make it a circle. So now I'm saying is that if x is in sharp P, so you should think of x as a sharp. Let me put here f. If f is in sharp P, then 1 over P f to the P minus f, that's also in sharp P. That's what I want to prove. And here is the proof. The proof is one line, and sounds like you already know the line. So let me do the line. So we take a circle. We take a circle of with P vertices, and we can color each of them with A colors. And so now we're looking at all colorings so in total there are A to the P colorings, of which A are monochromatic, right? So so now we subtract those are non-monochromatic colorings, because P is a prime. 1 over P is the number of orbits under rotation of these colorings. So number of orbits. Is this clear? let's do an example, because I think example is actually helpful. So, and it will explain what really happened. So where is, oh yeah. So for example, I don't know if you can see it. There's just one formula I want to write. So if 1 over 5, x to the 5 minus x is equal to 24 x choose 5 plus 48 x choose 4 plus 30 x choose 3 plus 6 x choose 2. Okay? It doesn't matter what these numbers are. What's important, they're all positive. Now, if they're all positive, each of those, for example, x choose 4, has a combinatorial interpretation. If x is the number of Hamiltonian cycles in subgraph, x choose 4 is the number of 4 tuples of Hamiltonian cycles, which are all distinct. Do you see what I mean? So, and it is not too hard to see that the same trick goes over here for general A, sorry, for general P. Yeah, and for and we conclude that observation over there. Do you see what I mean?
Sorry, how are those coefficients related to orbits?
So those are so those numbers are the number of different kind of orbits that you can get depending on how many same colors, different colors you have. So for example, 24 is actually 4 factorial. That's the number of all colorings being different. Okay. And so that's my clue that my time is almost done. So what happens from this point until the end is a long story. But let me tell you the end of the story. The end of the story is that, oh, I can use this one. So this is a theorem by Ikenmeyer and myself in 22. So I'm gonna tell you a very simple version of that theorem. Okay, and I'm never gonna tell you a non-simple version. So essentially, I'm gonna say that a polynomial. So suppose f is a polynomial in x1 up to xn. So f f1 up to fn in sharp p for all fi in sharp p. So this happens if and only if f can be written as a positive, non-negative integer combination of x1 choose 1 times ... xn. Well, x1 choose a1 ... xn choose an. So it turns out that those binomial coefficients is really the only thing you can get. Yeah, so this is that way I just denote a positive combination of all those monomials. It's a monomial. So all positive combinations of those are here. And so this is very and I'm a little bit lying, and I'm not telling you a lot of stuff. but essentially I'm saying that, so but that is the answer to the question. So essentially what I want to say is the closure properties of Sharpe functions are really only those polynomials that you can get. Okay? So so maybe I can just hint in the remaining couple of minutes. Let me give you a tiny hint of what are the difficult issues. The difficult issue is not when it's a polynomial by itself. The difficult issue is when you're dealing with inequality, what happens when you have constraints on the variables in the inequality. So suppose in fact those are not free. So those are not free variables. But suppose you have for all fi such that f1 plus f2 equal to f4 square. Okay, and that's where the difficult part comes, and we have a theorem which addresses that. So so what is the moral of this? The moral is that essentially modular certain computer science assumptions I'm not telling you. We know what is combinatorial and what's not if you're constraining yourself to polynomial inequalities. Okay, you should think of that as a kind of oblivious combinatorial interpretation. When you're asking to give a combinatorial interpretation to x minus y squared greater than 0, what I'm saying is, yes, we know that this is true, but we know, but there is a reason why there is no combinatorial interpretation for this difference. Is because if you put here generic Sharpe functions, it's not going to work. And we now, and essentially every time you're writing any inequality at all, what you're doing is, in addition to, one can ask 3 levels of questions. The first level of question, is it non-negative as a polynomial over reals? Second question is it written like that? Does it have a combinatorial interpretation? And the third question, is it non-negative as a sum of the monomials? And that is really the motivating question so for example, in our very latest work on the band conjecture, the whole work was motivated by trying to, I'm not going to tell you more about that too much or anything at all, but the whole work was motivated by us looking at these polynomials and trying to prove that it's actually that band conjecture cannot be proved combinatorially. You see what I mean? And so we knew that it's not monomially positive. We did not know if it's positive in this sense, and eventually we showed that it's not positive at all. But if there is one moral, is that one should always look, if any tool you're using, one should always use those tools and see if they can be made combinatorial. And that gives you some information of what you're doing. Okay, so in particular, this quadratic inequality that I showed to you as a special case of the Alexander-Fenkel inequality, this is saying that Alexander-Fenkel inequality is incredibly deep. It cannot be proved by simple combinatorial arguments. Okay, there are other ways to phrase that, but that's what this is saying. I think that's good for today. Thank you.
No, no, it's a diagonalization result. It's complicated. So yeah, but in general, this is a relative result. So no. So we prove it in the same way as all other diagonalization results are proved. Well, it's constructive. Deep down, it's constructive.
Whether x minus 1 y squared is easily not sum of binomials or sum of.
And if a polynomial isn't the sum of binomials.
Oh, yeah. You can just write it down explicitly. By those things, I forgot where they're written. They form a basis. Basis and polynomials. So you can write a monomial basis. You can write them in that. It's a single matrix. Yeah. So that's. Yeah. So it will take. It will take a while. So I have prepared a few more examples of kind of standard inequalities like Hadamard inequality, Cauchy inequality, and so forth. None of them are combinatorial, even though they're like completely elementary from geometric point of view. But from this point of view, none of them can be done. And sometimes you can prove it under weak complexity assumptions, but that's a relative version.
So in this last theorem, you probably also have to assume some non-collapsing of classes.
Let me not answer that. Yes. So you have to be careful here.
I have a very basic conclusion about what you've been talking about, what it actually means. So if you go back to this permanent inequality, let's take the permanent of a 0, 1 matrix. That's just counting the number of perfect matches.
Correct.
In a bipartite graph. So that's a problem in sharp P, right?
Yes.
If I give you any substantive edges, I can determine in polynomial time relativity, right? So the permanent of the matrix is itself in sharp P. But now you're not talking about that. You're saying I take the permanent of a matrix, and now for every matrix element, I'm going to plug in a function that's
correct.
Sharp P. Somehow, like, I don't understand the connection between those two points of view. Like, are they?
No, no, those are different problems.
So whether the deficit of the permanent inequality is itself in sharp P is a different problem from whether it's in sharp P when I plug in functions in sharp P.
Correct.
So which problems are we talking? I'm just confused. You seem to have jumped from one problem to the other.
Correct. You're right.
So what is the combinatorial interpretation? Which one of them?
So
I'm just confused about it. It seems that today you use a different definition of combinatorial interpretation than yesterday.
No.
Okay.
No. So at the end we're asking. So is the function that you get when you take a square of the difference isn't sharp P or not? And it's the same question as we had yesterday. So the main difference is that here for polynomials, I'm asking a question not for specific sharp P function, but for all sharp P functions.
It's a different question.
Yeah.
But so we could ask upstairs, if you go up one floor, there is an inequality.
Yeah.
Which, for example, if we were to restrict to 0, 1 matrices, is an inequality for mapping.
Yes.
You could ask whether the difference between the left and right hand side is in sharp P. And the theorem you wrote down doesn't say anything about
correct.
That. Is that right? Okay.
Correct. So hopefully Swihong will tell you about exactly the questions that you're asking.
No, okay.
In a couple of weeks.
I'm just confused because they're written
yep.
on the same board, right?
So what I'm trying, so somehow I'm trying to show different points of view on combinatorial interpretation. This is a completely different point of view from last time, but it's but you still discussing whether something has whether inequality has a combinatorial interpretation, and you're formalizing it still in the same way as a function that you get when you plug in sharp P functions is that in sharp P.
squaring it now. Take any polynomial in Sharpie function, that's another complexity function.
Correct.
What you are telling us is exactly when it will collapse to Sharpie and when it will.
Correct. So Avi said it best. As usual, maybe.
This question we discussed today is much further from combinatorics in some sense, right? It's much closer to complexity theory.
Yeah.
It's something about taking polynomials of already of things that are in some.
It's you might think it's so the way Avi said it, this is a problem in complexity theory, but the way I think about it, it's not. I kind of don't care what it's going to be as a class at the end. What I want to know if imagine you have a difficult theory for which you have a difficult proof. The proof has several ingredients. So you're proving some complicated inequality. Is the result in Sharpie or not? Is there a combinatorial interpretation for that inequality? Now you take each ingredient and you're asking, does that ingredient have a combinatorial interpretation? Can you reconstruct a combinatorial interpretation for the whole thing using this proof, mathematical proof as a guide? And I'm telling you, if you're using in the middle some polynomials which are not going to be in Sharpie in this sense, so which don't lie in this ring, then this is not going to work for you. So if somewhere in your proof you're using x minus y squared greater or equal to 0, then it's not going to be a combinatorial interpretation. So I'm basically I'm trying to build a theory of what combinatorial interpretations can be, and sometimes I can use simple properties like x minus y squared, and sometimes I can, and now in the future I can use more complicated polynomials. For example, if you have a polynomial x minus 1 squared, that's not going to be in that's not going to have a combinatorial interpretation, but it's not the same, but for a different reason than x minus y squared. So it is completely obvious that x minus 1 squared greater or equal to 0, but you cannot use the previous tool I had. And the clue here is that when you write it x squared minus 2x plus 1, you can write it as 2 times x choose 2 minus x plus 1, and there is this minus sign in front of x that shows that this is not a positive combination of those terms. So that's your clue that this is not a combinatorial. There is not going to be a combinatorial proof of this result. Okay? I'm basically giving you the recipe. And the recipe is when it goes to affine varieties, it's much more involved than what I'm saying, but I don't want to tell you that. This is all published in an 82-page long paper, I'm afraid. Yes. Yeah, that's what gap P means. Yeah, it's not obvious. It's but not super hard. I think.
One thing that the Sharpie minus Sharpie is not so bad.
I mean, some problems in there are good and some problems are not. So some problems are in Sharpie and some so gap P intersected with positive has problems which are not in Sharpie. But in practice, so to speak, we have other problems which require other polynomials of this kind. So that's what I'm trying to say. So if you got lost this lecture, next lecture, nothing like that at all is going to happen. I'm going to start completely from the beginning. And we're going to talk about posets and linear extensions. Okay, so I'm not going to talk about polynomials, but it is important to understand that we do, by now we have the whole theory developed for which we understand what is in Sharpie and what is not.
What you're saying is if your proof would apply not only to the particular Sharpe functions that care about and whatever they were, but the proof would be generic. It would treat them just as Sharpe. It would only use the property that they are in Sharpe. Then you will not be able to have a combinatorial.
Correct.
It's a restriction on some type of argument which in some proofs exist and in others.
Correct. So, so the way I think about it, it's not that much different from the original question when something isn't Sharpe or not, because that's also a restriction on some type of combinatorial arguments like injection.
I was trying to answer Ramon.
I understand.
Yeah, my understanding what Igor said, though he avoided saying it, so I'm doubting myself. When you say x minus 1 squared greater or equal to 0 does not have combinatorial notation, what you mean is that there exists some combinatorial quantity x, some quantity in Sharpe, for which x minus 1 squared greater than 0 doesn't have a combinatorial notation.
Correct.
Tell you anything about any given quantity you might care about.
So here I'm thinking of x as a Sharpe function, and I'm saying that in fact, for this particular case, this would lead to UP equal to co-UP collapse, but that's sort of not super important. So what I'm saying is that if x is counting something, then x minus 1 squared may or may not be counting something. But in full generality, if you substitute all functions here, it's not going to be counting anything.
It's in any given combinatorial involved, they'll have it's very just telling us certain arguments that cannot help us.
Correct. But again, just like the original problem, what I really want to understand is how far combinatorics goes. What can combinatorics prove? And combinatorics, unfortunately, is very weak. It cannot prove that. Which sounds a little strange because I love combinatorics. You would want a combinatorics prove a lot of stuff. But no. I think we're taking everyone's too much time from everyone. Thank you all.